going to cover examples 1 to 3 from notes 4.1, days 2 and 3. We're going to be focusing on analyzing rational functions. In the previous lessons, we looked at characteristics of rational functions from their graphs. We looked at x and y-intercepts, vertical asymptotes, and holes, and talked about end behavior in the form of horizontal and slant asymptotes. And we talked about why we get vertical asymptotes, why we get horizontal asymptotes. In today's lesson, we're going to be focusing on how to analyze a rational function, and our goal is going to be to determine x and y-intercepts, vertical asymptotes and holes, and horizontal and slant asymptotes. So let's get started. In this video, we're really just going to focus on x and y-intercepts and vertical asymptotes and a little bit about holes. So to find the y-intercept of the graph of any function, rational or not, we want to find the y value when x is 0. So that means we evaluate f of 0. To find x-intercepts of a graph, that's where the graph crosses the x-axis, which is where y equals 0. So we need to find x values for which f of x equals 0. But a rational function is a fraction. So remember, a fraction is 0 when its numerator is 0, but its denominator is not 0. That's because we cannot divide by 0. So to find x-intercepts of a rational function, we're going to look for values that make the numerator 0, but the denominator not 0. Okay? So to find x-intercepts, we find the real zeros. Remember, they have to be real to be x-intercepts of the numerator, and we exclude those values that are zeros of the denominator. Okay? These values are not part of the domain. In those cases, we're going to have either a vertical asymptote or hole at those values. And it'll be helpful to classify x-intercepts as having even or odd multiplicity based on the power of the factor that causes that x-intercept. Okay, so let's get started doing an analysis. I've got two functions in example 1. The first one is f of x is x squared minus x minus 2 over x minus 1. Whenever you analyze a rational function, first good step is to factor. All right, so I'm going to go ahead and factor this numerator, which will give me x minus 2 times x plus 1 all over x minus 1. Okay, and now let's do the analysis. So to find the y-intercept, I'll do that first. You let x be 0. So we're going to evaluate f of 0. It's easier to evaluate this from the non-factored form of the function because all those x squared terms and x terms become 0. So I would have 0 squared minus 0 minus 2 over 0 minus 1, which is going to be negative 2 over negative 1, which is positive 2. And I'm going to ask that you write y-intercepts as ordered pairs. So in this case, the y-intercept is the ordered pair 0, 2. Let's go ahead and find the x-intercept. So an x-intercept of a rational function is an x value that makes the numerator equal to 0, but the denominator cannot be equal to 0 because then that x value will not be part of the domain. Okay, so we want values to make the numerator 0 but not the denominator. So if I look at the factored form of the numerator, right, I have x minus 2 over x plus 1. So x minus 2 times x plus 1. This is my numerator. By the zero product property, the values that make that 0 are 2 and negative 1. So my x-intercepts are 2, 0 and negative 1, 0. And I should check, neither 2 nor negative 1 makes the denominator 0, right? Because 1 would make the denominator 0. And I want to talk about the multiplicity. The multiplicity of each one of these factors, x minus 2 has a power of 1, x plus 1 has a power of 1. So the multiplicity for each of these x-intercepts is odd. Let's go on to the next example. Example B, I've got x squared minus x minus 6 over x minus 2. Once again, I'm going to factor these. That will help in our analysis. So I factor the numerator as x minus 3 times x plus 2. And that's still going to be over x minus 2. Let's find the y-intercept. So the y-intercept, I need to set x equal to 0 and evaluate f of 0. Looking at the original function, the non-factored form is easier. I would have 0 squared minus 0 minus 6 over 0 minus 2, which is negative 6 over negative 2, which gives me positive 3. So my y-intercept, once again, as an ordered pair, is the point 0, 3. And to find the x-intercepts, I'm going to let the numerator be 0, and then make sure that the denominator is not equal to 0. So in this case, values that make the numerator 0, I've got my function is x minus 3 times x plus 2 over x minus 2. So by the zero product property, the values that make the numerator 0 are 3 and negative 2. So my x-intercepts as ordered pairs are x minus 3 and x, oh, I'm sorry, said the wrong thing. My x-intercepts as ordered pair are 3, 0, and negative 2, 0. And then their multiplicities of each of these is 1. So they're both odd multiplicity. And remember, their multiplicities are 1 because each of these is to the first power. X minus 3 and x plus 2 are to the first power. All right, so those are our x-intercepts. Let's flip the page. Talk a little bit about vertical asymptotes. Okay, so vertical asymptotes are of irrational functions are x values that make the denominator 0, right? So we're looking for values that are excluded from the domain, but the numerator not 0. This is how our textbooks describes it, but actually we're going to have a vertical asymptote as long as the multiplicity of that constant or that 0 is higher in the numerator. I'm sorry, higher in the denominator than in the numerator. Okay, so to find vertical asymptotes, we need to once again factor. So let's do the analysis, and I'm going to factor this numerator here, x minus same function we did before, x minus 2 times x plus 1 all over x minus 1. So to find the vertical asymptote, I'm looking for values that make the denominator 0. So I need the denominator equal to 0, but the numerator is not equal to 0, or the numerator has a lower multiplicity than the denominator. So in this case, my vertical asymptote comes from this factor right here. So my vertical asymptote is the equation x equals 1, and the multiplicity, this is first power, is odd. And once again, we're going to discuss what multiplicity does when we start graphing functions next week. Okay, so let's do the second function over here. So we had factored this before. I'll just factor it again. This is x minus 3 times x plus 2 all over x minus 2. So to find the vertical asymptote, we're going to find values that make the denominator 0, not denominator equals 0, but the numerator is not equal to 0. In this case, we're going to have a vertical asymptote at x equals 2. And the multiplicity, once again, is odd because x minus 2 is a factor with a power of 1. So multiplicity is odd. The last thing is in example 3, we're going to talk about why we get holes, and in the next lesson, you'll figure out we're going to go over how to find the holes. So this is more of an exploration. So I want to complete the table here for this rational function, x plus 2 times x minus 3 over x minus 3, and then also for the function g of x equals x plus 2. So if we start filling in this table, substituting -1 into the f function, if I put -1 in here, I get -1 plus 2 is 1 times -1 times -1 minus 3 is -4. So that's 1 times -4 over -4, which gives me +1. Okay, and if I put 0 into the first function, I'm going to get 2. And then if I put 1 into that function, I get 3. And if I put 2 into the function, I'm going to get 4. When I put 3 into the function, if I put 3 in here, I get 5 times 0 over 0, which is undefined. And if I put 4 into the function, I get 6. And I'm going to do the same thing with g of x. So when I do g of x, it's a little easier. -1 plus 2 is 1. 0 plus 2 is 2. 1 plus 2 is 3, etc. When I put 3 into g of x, I get 5. And when I put 4 into g of x, I get 6. So it looks like f of x is equivalent to g of x, with the exception of the point when x is 3, which is undefined in f of x, and is the point 3, 5 on g of x. So what we can say is f of x is equivalent to g of x, except at the point 3, 5. Where there is a hole on the graph of f of x. So this is why we get holes. When we have a common factor in the numerator and the denominator, like we have here, of equal multiplicity, when we simplified exponential expressions, we would have canceled out that factor. And then, once we simplified it, we would have said, oh, but we have to remember to write x is not equal to -3. I'm sorry, x is not equal to +3. Sorry, let me write that correctly. X is not equal to +3 because on the original function of f of x, we have a hole at 3, 5. On the simplified function, which we're calling g of x in this case, there isn't a hole. There would be the point 3, 5. All right, so we have a hole instead of a vertical asymptote. I'm going to write this down. So we have a hole instead of a vertical asymptote. Because x minus 3, that factor, is a factor of greater than or equal to multiplicity, of greater or equal multiplicity, in the numerator as in the denominator. Record. Okay, so let's graph the function. I'm going to graph f of x. I'm going to graph it in blue. Put these points on. So I have -1, 1, 0, 2, 1, 1, 3, 4, 4, 2, 4, and 3 undefined. When I graph that, I'm going to put a little open circle. That's going to be my hole. And then I have the point 4, 6. So this is actually the line y equals x plus 2 with a hole at the point 3, 5. This is our hole. This is the function we just graphed. So f of x is the original function, and g of x, f2 of x is like our g of x. You can see here's the line that we graphed, and the difference is the hole at 3, 5, where f of x is undefined, and f2 of x, which was g of x, has a value 5. But now I want to show you a couple rational functions. So if we look at this function, x plus 2 times x minus 3 over x minus 3, we'll expect to see a hole when x is 3. So down here, I can actually grab this point, and I can move it around. So as I move it around, it shows me the ordered pairs on the graph. So what's going to happen, though, when I get to x is 3? I should have a hole, which, boom, there it is. I have a hole at this ordered pair, right? I've got the function quantity x plus 1 over the quantity x plus 1 times x minus 2. You'll notice that we have a repeated factor of x plus 1 with the same multiplicity in numerator and denominator. Both of them are 1. So we would expect there to be a hole at x equals negative 1. So let's see what happens. I'm going to drag this point on the bottom, and it's going to show us our ordered pairs. And when we get to x is negative 1, it says a hollow point or a hole at when x is negative 1. But what's going to happen when x is 2? X is 2, it makes the denominator 0, which is undefined. And in this case, we expect to have a vertical asymptote. So I'm going to go ahead and continue to drag this along. And we'll see when x goes to 2, we have this vertical asymptote at x equals 2, where the ends of the function are shooting down when x is less than 2 to negative infinity, and then the function y is going to positive infinity as I approach 2 from the right.